A Boeing 767 loses all engine power at 41,000 feet, and instead of falling, it flies on silently for nearly 100 miles. This was not a fluke. Every airliner in the sky right now could do the same thing. A wing that keeps working long after the engines stop. A small propeller that appears out of the fuselage. A number written into every dispatch plan. And an industry that discovered more than once exactly how far a dead airplane can fly. When a passenger jet experiences a total loss of engine power, it does not plummet. It becomes a glider. This is because a wing generates lift from airflow rather than directly from engine thrust. In normal flight, engines have one primary function. They provide forward thrust to overcome aerodynamic drag. The wing itself does the work of keeping the aircraft aloft. As air passes over the wing, it creates a low-pressure zone above and deflects air downward below. This generates lift. The wing does not care if the engines are running. When thrust is lost, the pilot gently pitches the nose down, using gravity to pull the aircraft forward. Gravity replaces the engines, maintaining the airflow necessary to sustain lift. This exchange of altitude for forward distance is measured by the glide ratio. A typical modern airliner has a glide ratio of roughly 15:1, meaning it travels 15 feet forward for every foot of altitude lost. This performance is the physical equivalent of coasting a bicycle downhill for 2 miles after pedaling stops. Mathematically, this ratio is the horizontal distance traveled divided by the vertical altitude lost. Using a Boeing 767 as a working illustration, a glide ratio of 12:1 means the aircraft travels 12 feet forward for every foot of descent. This physical performance is comparable to coasting a bicycle downhill for 2 miles after pedaling stops. At a typical cruise altitude of 40,000 feet, multiplying that height by 12 yields 480,000 feet of forward travel, or roughly 91 statute miles in completely still air. Yet this theoretical reach is highly sensitive to operating variables. The actual distance changes based on aircraft weight, glide speed, wing configuration, wind direction, maneuvering turns, and the altitude that must be reserved to safely execute an approach. Achieving the maximum distance requires flying at the aircraft's specific best glide speed, a precise aerodynamic optimum of lift to drag, rather than a universal velocity. But if the wings alone keep it flying, why does losing an engine ever end badly? They could just glide to the nearest runway. But that is only the first reason. The second reason surprises almost everyone who learns about it. When jet engines fail, the aircraft loses far more than forward thrust. It loses its primary source of electricity and hydraulic pressure. Modern airliners rely on these systems to move their massive control surfaces, the rudder, elevators, and ailerons. Without power, the pilot cannot steer, leaving the wing's natural glide capability useless. To prevent this, engineers install a backup system called a ram air turbine, or RAT. This small wind-driven propeller automatically deploys from the belly of the aircraft into the rushing airstream. As the airplane glides, the forward speed spins the turbine, generating just enough hydraulic and electrical power to keep primary flight controls and standby instruments functioning. This emergency architecture preserves essential control rather than normal aircraft operation. The turbine is not an engine. It provides no thrust and actually adds aerodynamic drag. But it preserves the link between the cockpit and the wings, turning a descending aircraft into a steerable glider. On August 24, 2001, Air Transat Flight 236, an Airbus A330 carrying 306 people over the Atlantic Ocean, experienced a severe fuel leak in its right engine. The leak drained the aircraft's fuel reserves completely, causing both engines to flame out while the plane was still 65 nautical miles, or roughly 75 statute miles, from the nearest runway at Lajes Air Base in the Azores. When both engines stopped, the massive twin-engine jet lost its primary electrical and hydraulic power. At 24,000 feet, the ram air turbine automatically deployed from the fuselage belly into the windstream. The rushing air spun the turbine blades, generating the essential hydraulic and electrical power needed to run the basic flight controls and primary flight instruments. The Portuguese Aviation Accident Investigation Report confirmed that this system worked exactly as designed. The pilots established the optimal glide speed and steered the silent aircraft through a 20-minute descent toward the islands. Although the crew faced heavy control forces and lost secondary systems like autopilot and automatic brake modulation, they maintained steady command of the flight path. The unpowered Airbus reached Lodge's airbase and landed with only minor fuselage damage, completing the longest unpowered glide by a commercial passenger jet on record. The crew succeeded because they acted as disciplined decision-makers, managing a shrinking energy margin rather than relying on luck. The backup systems kept the flight controls functioning, allowing the pilots to steer. The RAT keeps the airplane controllable. It doesn't give back a single mile of range. Every foot of forward progress still had to be purchased with a foot of lost altitude. This may be the most critical reason, and it has nothing to do with aerodynamics. Here's the part that catches people off guard. Altitude is simply fuel in another form, a gravity-powered bank account that can only be spent once. When cruising at 35,000 feet, a jet holds an immense reserve of potential energy. In commercial aviation, this safety bank is heavily protected by strict regulations. Under Title 14, CFR, Section 121.639, U.S. carriers cannot dispatch an aircraft unless it carries enough fuel to reach its destination, fly to the most distant required alternate airport, and continue flying for 45 additional minutes at normal cruise consumption. These dispatch margins act as a physical buffer, ensuring pilots never have to manage fuel depletion and altitude loss at the same time. Yet a strict divide exists between pre-flight planning rules and actual in-flight emergency decisions. If fuel runs out at low altitude, the aircraft loses the vertical height needed to create useful horizontal distance. Altitude is the decisive margin. Without it, even the most streamlined wing is useless. On January 25, 1990, Avianca Flight 52, a Boeing 707 flying from Bogota to New York, entered a series of holding patterns. For over an hour, the aircraft circled in congested, weather-plagued airspace. As fuel levels dwindled, the flight crew informed air traffic controllers that they were operating with minimum fuel. However, according to the National Transportation Safety Board report, the crew failed to declare an explicit fuel emergency. Because of this critical communication breakdown, controllers maintained normal vectoring rather than clearing the aircraft for an immediate, priority landing. By the time Flight 52 was finally established on its approach to John F. Kennedy International Airport, the fuel was completely exhausted. One by one, all four engines flamed out. The heavy passenger jet lost all thrust at a critically low altitude. At 30,000 feet, a powerless airliner has minutes of time and miles of potential glide distance. At less than 1,000 feet, those physical options vanish. The pilots could not trade height for forward speed because they had no height left to give. The Boeing 707 crashed into a steep hillside in the residential community of Cove Neck, Long Island. The impact killed 73 of the 158 people on board. The aircraft did not experience an aerodynamic failure. Its wings and control surfaces remained fully capable of flight, obeying the same laws of physics that allow other powerless jets to slide safely to runways. The problem was not the wing's design, but the lack of space to use it. Theoretical glide performance requires a vertical bank account of potential energy to draw from. When that bank account is empty, the airframe can only fall. With no altitude left, there was no meaningful distance left to glide. Aviation safety is built on a dual philosophy: make a total power loss practically impossible, but design the airframe to survive if it happens anyway. With a global fleet logging billions of flight hours, regulators cannot promise absolute zero engine failures. Instead, they certify glide capability as an inherent tested property of the aircraft itself. Before any passenger ever boards a commercial transport jet, the manufacturer must prove its aerodynamic performance through rigorous flight testing. Under transport category certification standards, specifically those governing airframe performance, these glide characteristics are documented in the official flight manual. This means that a pilot facing an unpowered descent in an emergency is not guessing or inventing a glide path. They are executing a flight profile already mapped and verified by test pilots and aerodynamicists. The high aspect ratio wings and highly streamlined, clean configurations of modern jets are specifically engineered to minimize drag. allowing the aircraft to slice through the air with minimal resistance. Retracting the landing gear and keeping the flaps up maintains this clean aerodynamic profile. This design ensures that the aircraft can successfully trade altitude for distance at a precise, repeatable ratio. This documented capability turns a total power loss from a desperate gamble into a structured, predictable aerodynamic event. A powerless landing is a calculated physical outcome. It is the direct execution of a predetermined, mathematically proven flight path that was drawn on engineering blueprints and verified in wind tunnels decades before the flight took off. Every successful glide is a demonstration of physics operating exactly as designed under the strict supervision of global aviation authorities. Subscribe to the channel for more videos on the hidden science of aviation. This verified glide capability directly shapes how twin-engine airliners fly long-distance routes. Under a regulatory framework known as ETOPS, or Extended Range Twin-Engine Operational Performance Standards, aircraft are certified to fly hours away from the nearest airport over oceans or deserts. This system relies on the extreme reliability of modern turbofans and meticulous diversion planning. In an ETOPS framework, the primary plan for an engine failure is to fly to an alternate airport using the remaining engine. A total dual-engine loss is not the design baseline. Rather, the airframe's natural glide performance serves as an ultimate physical safety margin if everything else fails. The practical value of this fallback became clear on July 23, 1983, during Air Canada Flight 143. The Boeing 767, a brand new wide-body jet at the time, was flying from Montreal to Edmonton when both engines flamed out at 41,000 feet. A fueling calculation error where ground crews mistakenly converted fuel volume using pounds instead of kilograms left the aircraft with less than half of its required fuel. Suddenly, the crew was flying a giant, unpowered glider. At 41,000 feet, the aircraft was nearly 8 miles above the Earth, a height that acted like a massive physical savings account of potential energy. This altitude bought the pilots precious time and distance to troubleshoot and calculate a glide path. Managing their descent speed, they glided the 767 for approximately 45 nautical miles to a safe landing at a decommissioned military runway in Gimli, Manitoba. There were no fatalities among the 69 people on board. While the flight crew's skill was undeniable, their success was entirely supported by the laws of aerodynamics and the aircraft's engineered design. The incident exposed systemic human factor weaknesses, including unit conversion confusion, inoperative fuel quantity indicators, and a lack of training for total power loss. Yet, like other real-world fuel exhaustion events, it ultimately refined operational procedures without altering the underlying physics of flight. Survival in an unpowered descent relies on operational tools prepared long before the emergency begins. When primary systems fail, pilots do not guess. Instead, they turn to the aircraft flight manual, which publishes model-specific best glide speeds and performance data tailored to the aircraft's exact weight. On the emergency checklist, deploying the ram air turbine is the immediate step to secure hydraulic pressure and electrical power for the primary flight controls, ensuring the aircraft remains steerable. To protect every foot of glide distance, standard procedures dictate maintaining a clean aerodynamic configuration, keeping the landing gear and flaps retracted to minimize drag until a safe landing is assured. This physical margin is further supported by strict dispatch fuel reserve rules, which keep the altitude bank full before departure. Once in the glide, flight crews manage their remaining energy through tactical runway selection and constant wind awareness. This combination of pre-calculated engineering data and disciplined cockpit planning turns a silent descent into a structured recovery. It works when there's altitude to spend. But an airplane that runs dry on short final? Not at all. Mechanical failure is not the only pathway to an energy emergency. Often a sequence of ordinary decisions slowly erodes engineered safety margins long before the engines quiet down. Circling and holding patterns consumes precious time and fuel, dragging the aircraft down toward a progressively narrower set of options. If the crew fails to communicate their exact fuel state with standardized urgency language, controllers may delay priority routing, leaving both sides working with incomplete information. Even before takeoff, a simple unit conversion mistake can slip past pre-departure cross-checks, quietly setting a trap. Once the fuel is gone, pilots are forced to continuously calculate how many miles their remaining altitude can buy, knowing there is no option for a second attempt. It is the dangerous combination of a highly capable glider, the wrong fuel state, and the wrong altitude. This remains the ultimate operational challenge: an airplane that can always glide, and a fuel gauge that can still run out at the worst altitude. Modern safety systems focus on protecting the aircraft's altitude bank through early detection. Real-time fuel monitoring software now continuously compares actual burn rates against pre-flight projections, alerting crews before reserves are compromised. If fuel margins deteriorate, pilots rely on standardized communication protocols. Under FAA Order J 07110.10X, crews must use the explicit phrase "fuel emergency" to ensure immediate air traffic priority, correcting the communication failures of the past. To maintain operational readiness, regulatory standards recommend that turbine engine pilots practice dead-stick glide profiles in simulators at least once per year. Newer airframe designs extend this backup philosophy. Aircraft like the Boeing 787 employ auxiliary battery networks capable of powering flight controls for 30 minutes, reducing sole reliance on the ram air turbine. Researchers are also developing wind-aware routing software to calculate optimal emergency glide paths in real time. Ultimately, decades of operational history reveal a consistent truth: the physical ability of the airframe to glide has never been the weak link in the safety chain. Every flight we take today relies on this silent covenant between engineering and physics. When engines go quiet, safety is never a matter of luck, but a calculated conversion of altitude into distance. As modern aviation pushes the boundaries of efficiency, this built-in aerodynamic margin remains our ultimate safeguard. In the skies, we do not fly on hope, we fly on gravity, geometry, and disciplined planning.